Let's start with the simple definitions that we find in the National Electrical Code, or the NEC. And we're going to focus on Article 100, where most of the definitions are spelled out for us. Terminology is really important when we're communicating around grounding and bonding. So these definitions are going to be important so we're all speaking the same language. And what we're going to do is we're going to start with the term ground. The National Electrical Code tells us that ground is the earth. I think it's the shortest definition in the National Electrical Code. We define ground as the earth. So anywhere where you use the word ground, you're thinking you're tying to or you're connecting to the earth. Because the earth does not come with terminals, we have to establish a connection to earth, and we do that through what we call the grounding electrode. So a grounding electrode is a conducting object used to make a direct electrical connection to the earth. This is typically your ground rod, very common solution with regard to your grounding electrode. It could be your grounding grid, it could be the U for ground, or inside of a building it could be the structural steel, the water pipe coming into your home. Those are all grounding electrodes. And you could have multiple grounding electrodes at any one installation. And what the National Electrical Code tells us is that we need to connect all of those grounding electrodes together, and we create what the NEC calls the grounding electrode system. The grounding electrode system is when we pull all of those grounding electrodes together. So every grounding electrode that we have on that site, whether it be the U for ground, the water pipe, or other means that are identified in the National Electrical Code, we have to pull all of those together as a system. And that we call the grounding electrode system. Now let's talk about the grounding electrode conductor. This is the conductor used to connect the system neutral conductor or grounded phase conductor or the equipment to the grounding electrode system. Grounded, when we use the term grounded, this is when we say we are connected to the earth or to some body that extends that earth connection. Ungrounded is just the opposite, right? It's not connected to ground or to a conductive body that extends that ground connection. All right, so now we're going to talk about the grounded conductor. Now, this is the system or circuit conductor that is intentionally connected to the earth at that one point. We usually refer to this as the neutral. And its ugly brother, the ungrounded conductor, a circuit conductor that is not intentionally connected to the earth. So this is usually your phase conductors. Your grounding conductor. I know we're saying a lot of terms here with grounded conductor, ungrounded conductor. Now we're going to talk the grounding conductor. That's a conductor that is used to connect the equipment or the grounded circuit of a wiring system to a grounding electrode or to the grounding electrode system. Now, bonding and jumpers. So we're going to get into an area where we're pulling things together now. We're talking about bonding, and what the National Electrical Code defines bonded as connected to establish electrical continuity and conductivity. This is a very important term as we work throughout the power distribution system. Bonding conductors, or what we call jumpers. These are your reliable conductors to ensure the required electrical conductivity between metal parts required to be electrically connected together. Your service equipment, so when we get into service equipment, this is where your utility is connecting into the power distribution system. And in this equipment is where we're going to find some very important bonding jumpers. One of those is the main bonding jumper. The connection between the grounded circuit conductor and the equipment grounding conductor, or the supply side bonding jumper, or both at the service. So this is your main bonding jumper, that point where we pull both of those conductors or those systems together. Now your supply side bonding jumper, this is the conductor that's installed on the supply side of the service or within the service equipment enclosures, or for a separately derived system that ensures the required electrical conductivity between the metal parts that are all required to be electrically connected. Now we're going to move over to transformers. for grounding and bonding inside of transformers. When we move into a transformer, we're talking more like in a separately derived system. This is your electrical source or other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding connections. That's your separately derived source. So let's talk about that transformer. If I have a very common transformer you'll have in a power distribution system is your delta Y grounded transformer. There is an isolation between the primary and the secondary. You're establishing a separately derived system on the secondary of that transformer. And if we look over at a generator, you'll typically see people drive a ground rod next to a generator. And they'll bond the enclosure of that generator with that ground rod. If they connect the neutral to that enclosure inside the generator, they're establishing a separately derived system. Now, why is that important to understand that action will create a separately derived system? Because it will drive what you do in the transfer switch. If you bond that neutral to ground in the generator and you establish a separately derived system, you're going to need to switch the neutral in the transfer switch. And that would mean that you would need a 4-pole transfer switch instead of a 3-pole transfer switch. And if you're bonded in the generator and you're not switching the neutral, you have 2 separate areas where that neutral conductor is being bonded and you could have circulating currents. You could cause GFCIs or ground fault protection of equipment not to work and function correctly. A simple fix, if you didn't buy the right transfer switch, 3-pole transfer switch, and you bonded that neutral in the generator, is to just lift the bond in the generator. Your generator instructions will tell you how to do that. Now, we've established what a separately derived system is. And we know that depending upon, especially in the case of a generator, depending upon how you bond things in the generator and you establish a separately derived system, that will drive the solutions that you purchase and install. A non-separately derived system, good examples of those are your downstream panel boards or that generator that doesn't have an established neutral ground bond in there where you're using the 3-wire or a 3-pole transfer switch. Those are your non-separately derived system. You're keeping things separate. You're keeping your grounded conductor separate from your equipment grounding conductors in all of those locations. All right, so let's talk about the system bonding jumper. This is the connection between the grounded circuit and the supply side bonding jumper. So we have a grounded circuit conductor out there. We have a system ground where we're establishing our ground, and we're going to need to bond those two together, and that's what this is all about. Your equipment bonding jumpers, these are your connections between 2 or more portions of the equipment grounding conductors. We have to make sure that we bond everything together, and anytime we put jumpers in between your equipment grounding conductor and any of the steel that needs to be bonded, those are your bonding jumpers. Equipment grounding conductor. So we've used that term, let's define it. The equipment grounding conductor is the conductive path that is part of an effective ground fault current path and connects metal parts of the equipment to the system neutral or grounded phase conductor. And that's done back in one location. Think of this as that bare copper conductor that you carry out to all of those loads. Or if you open up any receptacle, you'll see that bare copper conductor that's in the receptacle outlet. That is your equipment grounding conductor. We want that to be a low impedance, and we want that to carry fault current should a fault occur, a ground fault occur in the system. All right, so everything that we've talked about so far has been about grounding and bonding of components and electrical systems. We're establishing that connection at the service or at our separately derived system between the grounded conductor and our equipment bonding and ground and earth. Now we're going to talk about system grounding, and we're going to hit solidly grounded systems versus resistance or impedance grounded systems. Solidly grounded, when we use that type of terminology or that type of a system, we have a solid connection to the earth at some point in the power distribution system. There's no resistor or impedance inserted in that connection point. Ungrounded systems are just that. There's no connection to ground or a conductive body that extends that ground connection. We're insulated from ground. Your impedance or resistive grounded systems. These are systems that are connected to the ground, to the earth, through an impedance. All right, last statement about grounding, objectionable currents. Now, we use this term objectionable currents in Article 250 of the National Electrical Code, but you know there's no definition in the NEC. And when there's no definition, you know what you do? You make it up. So this is my definition. Current flowing on the effective ground fault current path during a non-faulted condition. And I think to best understand this, let's just talk about an example that you are probably well aware of because it received a lot of attention over at least the last 2 cycles in the National Electrical Code. And these are those motion sensor switches, type switches, that you'll find in either residential homes or commercial buildings, where you walk into a room and it turns the light on. If you think about how we wired residential homes or any types of structures when we came down to a light switch, what did we do? We brought one set of conductors, and that was our hot conductor. And we brought an equipment grounding conductor as well. And we did not bring a neutral. When we had a standard light switch, that was perfectly fine because we're just breaking one conductor. But when you install a product like a motion sensor switch, which needs to have power, so you need a neutral conductor to provide the potential voltage to power up electronics. If I opened up a light switch and I don't have that neutral conductor there, I could get that power by taking hot to ground, the equipment grounding conductor, to power up that unit, and it will work. But it would put current over the equipment grounding conductor. And based upon the definition that we just created and just talked about, that would be current flowing on the equipment grounding conductor that's not because of a faulted condition. That would be what we call objectionable current. And that is not permitted by the National Electrical Code. So changes have occurred over the last few cycles, 1, to prohibit the use of those products, and 2, to require the pulling of a neutral at those switch locations. So in case you installed a technology that required to be powered up, you're not likely to grab that equipment grounding conductor to get that done. You will properly use the neutral grounded conductor to get that done. So hopefully that helps you understand what we mean by objectionable currents. And remember, all of these terms that we just talked about, it's critical that we use these terms correctly as we communicate to make sure that we all understand each other and we get things right. And hopefully this little review helped you.